calculus, like I said, I'm going to be introducing it as a very broad topic. So looking at calculus as a whole, and then we'll go into exercise 17A, which is going to be our first exercise for calculus. So calculus is a very, very particular topic. And back in the 1600s, it was the biggest new thing. What is calculus? I know some of you have heard of it before. Can anyone tell me what is calculus? Anyone? Anyone have guessed what calculus is? Danuka, in your own words, what is calculus?
Where you put a tangent to a curve and then...
That is a very mathematic approach. I like it. But in a broad sense, let's pick one topics that we're already familiar with. What is probability?
Chance.
Thank you very much. Study of chance, right? What is algebra?
Numbers.
Numbers. What else?
Unknown.
Algebra is to do with unknowns, variables. Variables are to do with relationships. Yeah? Algebra is to do with relationships, probability is to do with chance. Now, calculus is anything that changes. Calculus refers to change. Now, what is the word calculus, or where does it come from? What does the word calculus sound like?
Calculator.
Calculator, what else?
Calculation.
Calculations or calculate, yeah, what else? Think chemistry. Calcium, thank you.
Yeah, I was going to say that.
It's weird, isn't it? What about, have you guys been to the dentist and they've told you need to prevent building up calculus in your teeth? No, never heard of that before?
Celsius.
Celsius? No, that's not as relevant. Calculus. Okay, so when they let's start with a very broad question. Why do you brush your teeth every day?
Keep it clean.
Keep them clean. Why every day though? Why not just brush them once a week?
The plaque builds up.
Thank you. The plaque or the tartar, right, builds up, and over time, if you don't brush it away when it's soft, it becomes calculus. Calculus is really tough, like rock that's stuck in your teeth and builds up on your teeth. It's really weird. But yeah, you don't want that stuff, so you brush it every day. Calculus comes from a Latin word meaning small pebble. Now you can guess why calculus in terms of the teeth comes from the word small pebble. It's a Latin word. But calcium as well, it's a mineral, looks like a small pebble. The reason why calculate or calculators and calculus comes from the Latin word small pebble is because back in the olden times, Greek times, whatever, they used small pebbles to do math. And it was called an abacus. You guys heard that stuff? Yeah, ancient math, isn't that weird? So, calculus comes from the Latin word small pebble, and we're going to be looking at it in a broad sense. So, calculus was developed in about 1700s by two people. One of them that is very famous, hopefully you've heard of, Isaac Newton. Surely you guys have heard of him. And the other one was someone that you probably haven't heard of, Gottfried Leibniz. Okay? Now, I know it sounds really weird. Back in those times, finding like a mathematic discovery is very, very important. It's like your breakthrough in life, the reason you were born or whatever at the time. Isaac Newton and Gottfried Leibniz both agreed. They both found some sort of way to describe. They both came up with calculus, basically. Right? They came up about the same time. The general consensus nowadays is that they both independently came up with those ideas, but they both argue that one person stole off the other. You guys get how it is. But about the same time. Like I said, calculus is the study of change. We're looking at, can we determine how fast something is changing? Now, you guys already heard that in terms of linear equations. How do I determine how fast something is changing? It's called starts with G? Gradient, thank you. Starts with gradient. But let's look at it from Isaac Newton's perspective. Newton said, there's a lot of... Isaac Newton was a physicist, by the way, just in case you don't know. Isaac Newton was looking at inversely proportional laws. What does inversely proportional mean? Also, am I talking too quickly? What does inversely proportional mean?
When one goes up, one goes down.
Good. As one goes up, when one value goes up, the other value goes down. That's what inversely proportional means. Proportional just means as one goes up, the other goes up. But there's a lot of laws in our understanding of the physical realm that are inversely proportional. For example, Isaac Newton found that the force of gravity, I'm just going to write force here, the force of gravity is inversely proportional to the distance. Well, technically distance squared, but we'll just leave it as distance for now. As the distance increases, the force decreases. It makes sense. The further away you are from a planet, the weaker the gravitational force. Same idea. If I was to go closer, as the distance gets smaller and smaller, the force increases as well. So he ends up with this equation right here. Okay? Ends up with that equation right there. He says, I like that I can find, by graphing this, I can find what is the amount of force, a gravitational force that a certain thing feels at this distance or this distance, something you guys already know. As I let my x equal to 3, what is my y value? You guys already know that stuff. Isaac Newton then said, how do I find how quickly it's changing at that certain point? So instead of just saying, what is the force? How much is the force changing by? You guys already know that if I was looking from left to right, if I pick that point right there, you know that the force is decreasing in speed. Makes sense? Right? Decreasing in rate of change, sorry. He said, how can I find a mathematical way to prove or find an equation that exactly tells me the rate of change at that certain point? Guys, chill. So he developed this idea. He said, what if I drew a circle? I've drawn better. Let's pretend that that's a perfect circle. He said, if I pick this line right here, this is what we call a secant, my intersects are this point and this point right there. Agreed? Yeah. Let's focus on the circle. I pick 2 points and I find rise over run. That's my gradient, isn't it? That'll come in very important later, so remember this. M equals to y2 minus y1 over x2 minus x1. You guys have seen that before, hopefully. So the gradient of the line. Now, it's very, very, very easy to find the gradient of a straight line because the gradient of that line doesn't change. If I was to give you a straight line that looks something like this, it doesn't matter where I pick those points. It could be here and here, or here and here. It doesn't matter how far or close, whatever they are. The gradient's always going to be the same. Agreed? Awesome. Now, he said, what if I wanted to find the gradient at this point right there? So I can draw parallel lines and get closer and closer. So we know those 2 points there. Would you agree it has the same gradient as this line right here, assuming that they're parallel? Yes. Yeah. Now it intersects are slightly closer. Do the same thing. My intersects are slightly closer. Agreed? The distance between the intersects gets smaller and smaller, or the points rather, until a certain point where they're so close that it only touches the circle at one point. That's called a tangent. Thank you very much. It's called a tangent. Our whole understanding of tangents from trigonometry comes from circles, but we'll talk about that later in the video. So it's called a tangent. By definition, a tangent is a line that has the same gradient as my curve, but it only intersects at one point. Does that make sense? Yeah? So it's a tangent, it has the same gradient as that point. So now Isaac says, instead of trying to find the gradient of every single point, why don't I try and calculate the gradient of this tangent at that point? Does that make sense? Yeah, I feel like I've lost some of you. Are we all good? Okay, let's continue. So, what is the difficulty of finding the gradient of this tangent right there? We only have 1 point, don't we? Because it only intersects the curve at 1 point. Can we use this gradient formula when there's only 1 point? You can't. But my question is, why not? Yeah, go for it. It does need 2 points. It's rise over run. That's our formula, isn't it? Gradient is rise over run. If my run, actually, my question, what is the run? How far has it gone to the right or left? 0, right? And I think I've talked about in the past, you can't divide by 0. You guys know that, yeah? What happens if you divide by 0? Infinity? No. Answer is undefined. It doesn't exist. I don't think I've talked about this before, have I? It's too many answers, you're right. But the idea is you can't divide by zero, it doesn't exist. It's not that it is infinity or negative infinity, it just doesn't exist. So we can't divide by zero. In other words, we can't have only 1 point. Guys, can you close your laptops? You don't need your laptops for this session. Thank you. You can't divide by 1 point. So what Isaac Newton developed was something called limits. Okay? So he said, let's focus back on this line right here. He said, if I draw a line, let's say I draw this line right here, I want to find the tangent or the gradient of this line at that red point there. He said, what if I draw a tangent like this? Okay? Well, we can say that, oh, that's not a tangent, sorry, it's a line. We can say that that line has an approximate gradient to that point there. We know that tangent would actually look like this. It's not exactly the same, but we know it's close. If we smaller that gap, let's say I pick this point and that point, I draw my line there. Close, it's closer, not exactly close. I can keep going, where I make those gaps smaller and smaller until it's the same as that line there. Okay? As you make that gap smaller, we can actually find that gradient. So, he said, let's propose the idea of limits. Now, has anyone here heard of limits before? Can I just get a slight nod of the head if you have? Limits, he said, let's not actually set the run as zero. Let's say it's very, 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 very close to zero. Okay? He said, well, limits show us that we can approach a certain value without actually getting to that value. But I'm not going to cover that yet. I want you to just keep that in mind. I'm going to draw a very basic, just a basic curve. Okay? Looks like this. Let's call it f of x. You guys are familiar with that. Let's pick a point. I'm going to pick this point right here. Let's call this one x. Okay with that? Lovely. If I substitute x into f of x, what's my y or my value going to be? It's just going to be f of x. Right? If I sub in x into f of x, we get f of x. Let's pick another point. Let's pick this point right here. That point, let's say, is h distance from our original x value. Yeah? So my new value is x plus h. Are we okay with that? Lovely. If that's x plus h, if I substitute that into f of x, what do I get here? Thank you very much. F of x plus h. Now, conventionally we use h. You can think of it as height, but it doesn't really make sense. Just remember h. So what we've done is we've created 2 points in this line. Now, it doesn't matter exactly where they are, because we've just used variables, algebra, to substitute a point in. But we're saying, well, how do I find the gradient of this line? Assuming we keep that h value. So the gradient we know, m equals to y2 over y1 minus x2 minus x1. Yeah? So I go y2, let's pick this y value, f of x plus h. I'm going to take away y1, which is f of x. Are we following along? Yeah. Divided by x2, which would be this x plus h value. Take away x1, which is just x. Now, by simplification, I know that I can just cross these ones out, can't I? Positive x and negative x cross them out. And we end up with this equation here. F of x plus h, take away f of x over h. Now, like we mentioned, Isaac wanted to make this gap h as small as possible. Because the smaller that gap is, the more accurate our gradient is going to be. But the issue is you can't let h equal 0. Otherwise you end up with some undefined value. So what he did was he developed limits. I'm going to write the limit as h approaches 0. The limit as h approaches 0. So in other words, as we write this equation here, we're going to try and make it so h, that value of h, is as small as possible. Or that distance between those two gaps gets smaller and smaller and smaller and smaller. Does that make sense? So this is what we call first principle. Some of you might have heard this before. It is a very, very redundant equation, but it was very, very important to learn. This came up in the 1700s. It was only later until we discovered a certain formula for it. But like I said, we'll talk about that later. Now, this limit allows us to actually substitute h as 0 without really substituting h as 0. I'm going to go through an example. You guys mind if I rub this off? Okay. So Isaac Newton developed this terminology. He said that instead of writing m, because we know that's a gradient, I'm going to write that as f dash x. F dash meaning the differentiated version of f of x. Now, it makes sense that if I was to write two dashes, it'd be the derivative of the derivative, but that's not as important right now. So we know that f dash x equals to that, but Gottfried or Leibniz had a different kind of notation, because remember, they developed it independently. He said, well, y2 minus y1, that's just going to give us this gap right here, isn't it? That's the whole point for the rise. So he said that y2 minus y1 is the same as the difference in y. And in ancient Greek letters, they used delta to symbolize that difference. Those of you that do physics might have heard that before. Same thing, x2 minus x1 is that distance between here. And so we end up with delta x. And in modern day terms, you write dy dx. That's what that comes from. So, let's use the example of y equals to x squared. What I'm going to do is I'm going to substitute these values in order to try and find an equation that helps to find the gradient. So, y equals to x squared. I'm going to use that formula right there, where we've got the limit, or f of x, equals the limit of h going towards 0, of f of x plus h plus f of x, minus f of x, over h. Let's substitute our values in. I get f of f dash x, equals to, and I have to keep that there for now, limit as h goes towards 0. What is f of x plus h, if f of x or y is x squared? Well, I substitute x plus h wherever I see x. So instead of writing x squared, I write x plus h squared. Does that make sense? Minus, now instead of writing x, I write x. In other words, it's the same thing, right? So I'm substituting x as x, or just writing f of x, which gives us x squared. Have I lost anyone? I feel like I went through a whole roller coaster. Divided by h. What is the issue with this equation here if h was 0? What is the issue?
You can't divide it.
Can't divide. So we have to change something. Let's expand it and factorize and simplify, blah, 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 in order to get h off being the bottom. We don't want it to be on the bottom. That's the whole reason why Isaac developed limits. Let's go ahead and expand it. Equals the limit of h going towards 0, x squared plus 2hx plus h squared minus x squared over h. Are we okay with that? All I've done is just expanded that, so we get x squared plus 2hx plus h squared. That's just that expanding using the formula. From there, I know that I can simplify. I'm going to cross out my x squareds. So I've got plus x squared and minus x squared. And we end up with the limit as h goes towards 0 of 2hx plus h squared over h. Is there one more way I can simplify that? What is it? No. I know that I can
Divide by h.
take out h. So I get the limit as h goes towards 0 of h bracket 2x plus h over h. Would you guys agree the same thing? Yeah. Now I can simplify, can't I? I'm just going to go ahead and cross these out, and I end up with, I'm going to rub this out, end up with the limits, I know it's a long process, isn't it? The limits as h goes towards 0 to x plus h. Is there a h in the bottom anymore? Are we divided by 0? No, we're not. Now, we can substitute h equals to 0. And we can take out the limit as h goes towards 0 now. And we can literally substitute h as 0, and we get 2x. In other words, f dash x equals to 2x. What we've done is found an equation that no matter what point we put in, we can find the gradient of that point on y equals to x squared. I'm going to jump a few hoops. I'm going to go ahead and show you what that means. So let's go ahead and draw our graph of y equals to x squared. Okay? Marissa, give me a value of x. Any value. 3. Let's do 3. So x equals to 3. What is my y value then? Well, it's just 3 squared, so it's going to be 9. Now we can find the gradient of the tangent that passes that point. So let's assume that's the point right there. My tangent is going to look like, oh gosh, it's going to look like that. Very, very positive, isn't it? Yeah? Let's use our equation to substitute that in. So remember, f dash x, or derivative, which is the same as writing dy dx, by the way, is 2x. If I write f dash of x being 3, I get 2 times 3, which gives me 6. That means the gradient of that line is 6. In other words, that at that specific point, the gradient of that line tells me that for every 1 unit it runs across, it runs up 6 units, which is very positive. Does that make sense? Have I lost anyone? Does anyone have any questions? Yeah, go for it.
I'm a bit confused. How did you get from the 2x plus h to just 2x?
Yeah, so I got rid of the limit because I know that there's no longer h in the bottom. Because the biggest problem was there's a h in the bottom I can't divide by 0, right? So I simplify, factorize, blah, 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 and I get to this. And because now there's no h in the bottom, I can get rid of this limit as h goes towards 0 and literally substitute h equals to 0. Because the goal of this is to tell me that h is going towards 0 without actually writing h equals to 0. Once we get to this point, h is allowed to be 0. We don't end up with an undefined equation. So from this point, we can get rid of that, literally substitute h as 0, and just write 2x. In some situations, you might have, let's say, 2x plus hx at the end. Same thing, you substitute h as 0, and you'll just get 2x. Any other questions? No? Sweet.